Hey everyone, Morgan here. So we're going to be picking back up with the lecture outline on light at page number 4, and this rather cryptic question of what do beer, football, and the 1908 Olympics have to do with chemistry. And I think it's important to understand that political events shape science, science can shape political events, and this was really the case back in the early part of the 1900s and the development of quantum mechanics. So we're going to start off with this picture, which is the bright line spectrum for hydrogen. Now, I made a really big deal in the last lecture talking about the differences between a continuous spectrum and a bright line spectrum. Now, a continuous spectrum would be created if our source of light here was what we call white light, a mixture of all wavelengths. But in this case, we're doing it with a gas discharge tube, and it just contains hydrogen. If we used a different element, we would actually get different sets of lines. But this is a very well-known spectrum. It dates back to the mid-1800s, and we need to start getting our butts in gear for explaining why does this happen? Why is it different than a continuous spectrum? Okay, so Johann Balmer in the 1880s, a Swiss high school teacher, was actually able to come up with an equation that would predict where these lines should fall. This is the equation itself. 1 over lambda, or what we call the wave number. I made a big deal about understanding wave numbers in the last lecture, is equal to a constant times 1/4 minus 1 over n squared. Now, sorry folks, but this is y equals mx plus b, isn't it? And that constant is the slope of the line. Okay? Now, the value of n for this specific one, for the hydrogen spectrum, the n would take the values of 3, 4, 5, and 6. And it's a very linear thing, easy to graph. So your question should be, what does n mean? And that was the problem. We actually didn't have a decent description for n. We didn't have any description. We just know it fit the data. So not unlike what you saw with Max Planck in 1900, we had data. We had a relationship to describe the data. You got it by graphing, okay? But we didn't quite know what it meant yet. So it was expanded a little bit by a university professor who saw this and then started to look in other areas of the spectrum, beside, outside visible light, because that's all that Balmer had the equipment to look at. Okay? So once Rydberg looked at some of the infrared parts of the spectrum, he found more lines. And he was able to expand the equation to look like this, with a restriction that that number you see, n final, is always smaller than n initial. And the n's are always nice whole numbers. Okay, great. Found more sets of lines. What do they mean? He had absolutely no idea, but he knew it fit the data. Okay, so this constant I've presented to you as wave numbers, which is a very historical value. And it's actually the one I still use when I'm doing problems based on this. But for most people today and for the AP exam itself, it's going to be presented as 2.178 times 10 to the negative 18th joules, okay, to get it into a more modern unit. It's printed on the exam, don't worry about that. Okay, so now let's see if we can summarize all of the different sets of lines that people were finding and the numbers that described them. First, we have the Lyman series, where n final is equal to 1, and n initial would be 2, 3, or 4, fell into the UV region. The Balmer series, where we already said n final equals 2, n initial would be 3, 4, 5, or 6. Okay, visible light. One called Passion, one set of lines, where n final is 3, n initial is 4, 5, or 6, falls in the near IR. That means it's near visible light. Bracket series, which falls in the IR, and the Fund series, which falls in the far IR. Now, every time you were getting sets of lines that basically looked the same as the Balmer series, except you couldn't see them with the naked eye. You needed special equipment because they were falling in the UV or in the IR. Now, important to point out, my OCD is just loving this table. Everything is right where it should be, following a specific order. Second thing to point out, the Lyman series falls in the UV. That would be the highest energy. And the Fund is in the far IR, which would be the lowest energy. So pause if you have to get this table filled out. Okay, what's it all mean? Didn't know. So let's fast forward until about 1910, okay? Good 20 years later. And a guy named Niels Bohr out of Copenhagen, which is in Denmark. It's a great city, you need to visit it, okay? He is a very well-educated child of university professors, also well-educated, very well off, okay? And he gets a chance to go and work for J.J. Thomson as a postdoc at the Cavendish Labs. Now, he was not thrilled at this situation. He and Thomson did not get along well. And the night before he was going to quit and go back to Copenhagen, at a class reunion type event, he met Rutherford. And Rutherford, who had been a student of Thomson's, gone to Canada, McGill University, okay, there, developed a really great lab, got the chance to come back to England and do the same thing at Manchester University, okay, real popular football city, if you're not aware, okay, Manchester United, but most of you are probably aware of them. So over that discussion, Rutherford realized that Bohr was familiar to him. Rutherford had watched Bohr's older brother play football in the, we call it soccer, in the 1908 Olympics in London. And he, mistook him for his brother Harold. And, Bohr straightened it out pretty quickly. But in the conversation that when happened, Bohr became enamored with Rutherford's planetary model of the atom. And he decided that he was going to go up to Manchester and finish out the last year of his postdoc with Rutherford. Also a chance to watch, the Red Devils play, go Manchester. And when he left and went back to Copenhagen, he was now a big proponent of this new model of the atom. Now, as he was setting up his laboratories in Copenhagen, several things just happened to converge on the same point that made his discovery possible. One, his lab was going to be sponsored by the Carlsberg Brewery. And Carlsberg was the owner, the operator of a pretty amazing place called Tivoli Gardens, which is basically an amusement park. So his laboratory was there. And as he was interviewing, potential staff members, new professors to come in, etc., one of his former classmates from his undergrad asked him if this new theory could help to explain the Balmer formula. Okay, and this was something that Bohr was not overly familiar with. So after it was explained to him, Bohr realized that this was the connection that he was looking for. And in a very short amount of time, was actually able to work out all the details of a new model of the atom, okay, that would correctly explain the bright line spectrum. So in Bohr's model, what we have, we will call well-defined circular orbits. And when the electrons transition between the orbits, they either absorb or release set amounts of energy, depending upon the size of the jump. Okay, you see this pretty well in this diagram over here on the right. And then you're seeing below it what might look like bright line spectrum lines. So it turns out the smaller jumps, like the 2 or the 3 to 2, would release red light, which is low energy, but a bigger jump, like the 4 to 2, would correspond to the green light. Or the larger the jump, the higher energy the light that was going to be given off. Okay? Now, these colors would never change because in Bohr's model, these are well-defined circular orbits. Their sizes never change. So you'd get the 656 line that you saw, the 486, the 434. You're starting to get the idea here. Okay? Now, this is pretty straightforward. Okay? And people bought into this theory really quickly. And Bohr ended up getting the Nobel Prize eventually, about 1920, I think, for the concept of well-defined circular orbits. And all of this came out and published in 1914. Okay? Now, we often say that this is the best wrong idea ever. There were problems with Bohr's theory. There are parts of it that are perfectly reasonable and really quite correct. But they turn out to not be well-defined, they turn out not to be circular, and they turn out not to be orbits. But besides that, it's pretty cool. So don't worry. You'll see the details in a few minutes. You'll understand why this is actually kind of humorous. Well, 1914 also saw some interesting other things happening in the world. Archduke Franz Ferdinand, who was the heir to the Austro-Hungarian Empire, was killed on June 28th by a Serbian anarchist named Gavrilo Princip. Okay? And because of a specific set of treaties that happened to exist, what ended up happening was World War I and the eventual end of the Austro-Hungarian Empire. Now, physics research was pretty much going to come to a halt because most of the people doing physics research were drafted. Okay? Now, at the end of the war, the armistice was called at 11 a.m. on the 11th day of the 11th month. And we currently celebrate November 11th as Veterans Day in honor of this. Now, the Treaty of Versailles itself was not kind to the country of Germany. And it ended up really being the cause of World War II. But in a very brief, specific period, 1920 to about 1932, 1933, German science flourished. And really, we got some amazing discoveries that furthered Bohr's ideas. But you have to understand that post-war, it was a new generation of people that were going to be working on all of this science. Well, interesting things to understand about the differences between World War I and later conflicts like the Vietnam War. Okay? It was possible during Vietnam to get out of the draft and out of having to serve by being wealthy, which means you could be enrolled in school, an approved major, an approved GPA, and they wouldn't draft you. Okay? So in World War I, that wasn't the case. And in fact, some of the first people to sign up and serve were those that were wealthy and well-educated. Okay? So a lot of the physicists went straight from labs to battlefields. And I would encourage you to go look up a guy named Henry Moseley, who we generally credit with naming the proton. He was killed at Gallipoli. And a lot of people believe that he was actually smarter than Einstein. And had he not died, he probably would have reshaped science a lot more even than he already had. Okay? But serving in World War I, if you were from a position of power, it might actually influence where you served. And that was the case with a guy named Louis de Broglie. And that is the correct French pronunciation. Don't say Broglie, it's Louis de Broglie. Now, Louis, his great-great-grandfather had actually served under George Washington in the Revolutionary War. And de Broglie's entire family had been part of the French aristocracy. He was actually, his title was Prince Louis, and eventually moved on to Duc Louis, which is the equivalent of the English word Duke, when his brother passed away. And de Broglie, well-educated, already had a PhD in like French literature and that, was just the right age to serve in World War I. But his father was able to get him a position working as a radio operator. And it was at this point where he really fell in love with the concept of radio and electromagnetic radiation, which led to some really seminal work post-war. So what had happened was that he ended up being stationed here. And these are the Paris catacombs. Now, there's an extensive, several-mile-long tunnel system that runs beneath Paris, where they have mined marble, limestone, etc., out of the ground for centuries. And all the palaces and that were built there were built out of this. And these empty corridors started to be used in the late 1500s because of plague. And during the plague years, what happened was the Paris cemeteries filled up, and they had to empty the cemeteries of the bones. They needed a place to put them. So they recreated certain cemetery conditions in different areas of the catacombs. You can see here in the picture on the left that, these were removed from a specific cemetery on a certain date. Okay, and this has gone on for a long time. This is really kind of a spooky place. I've walked through this. It's been almost 20 years since I've been there. I've also been to some catacombs in places like Rome, but the Paris ones are the spookiest and the coolest to visit. See, but because they're spooky and cool, that's where the French resistance and the French army set up their base of operations for radio broadcasts. And it's still a new thing. So when the enemy would start to go into the catacombs, if they knew how to find their way in to begin with, you could hide behind all of these stacks of human bones. And it was a really great place to conceal yourself. So after the war, de Broglie, enamored with radio waves, went and got a PhD dealing with physics. It was his second PhD, actually. And what he showed was that light has momentum. And since light has momentum, he developed this equation to measure the wavelength of the light. Lambda equals h over mv, and mv is the equivalent of momentum in physics. So if light has momentum, that means light has mass. And if light has mass, that means it is a particle. But what this also means is that all particles have a wave-like nature. You can measure their wavelength. All matter is wave-like. So when his dissertation was presented, it was a little controversial, and it took a few outside sources, most specifically Einstein, to look at it and to say, okay, this is possible. And as best I can tell from my research, I spent a lot of time reading about the Nobel Prizes, a lot of this because I'm a stamp collecting. De Broglie is the only person in history to receive a Nobel Prize for his PhD dissertation. So he presented this work in 24, and then I think it was in 27, maybe 29. So two fast calculations. You're not going to be responsible excuse me, for doing calculations like this, but I want to show you the results of it. If you measure the de Broglie wavelength of an electron, what you find is that wavelength is basically 10 to the negative 12 meters. Now this is actually, I would say, 10,000 times larger than the electron itself. So that means you would actually notice the electron going in an up and down pattern as it moved. But if you do the same calculation for something like a baseball, it turns out the wavelength is incredibly small, 10 to the negative 34th meters. So incredibly small compared to the size of the baseball. And you're not going to notice the baseball going up and down. Okay? So the difference here is that this concept matters very much for subatomic particles. It doesn't matter for things like Cadillacs and rocket ships and baseballs and soccer balls. So, the Broglie wavelength is important for an electron, but not important for baseball. That was the point of those two numbers. And AP exams never actually asked somebody to calculate a Broglie wavelength or anything like that. Okay, so that pretty much takes us through the pages, I believe it was 4, 5, and 6 of your lecture outline. Okay, hope that worked out well for you. That's kind of the crash course version. A lot of the cool and interesting stories from the lecture I omitted just for the sake of making this a more manageable length video for you reviewing. Okay, thanks for tuning in. This is Morgan, signing off.